Wow, so a lot of people are really butthurt over my flat Earth video. Well, idiots are at any rate, because you pretty much have to be an idiot to think the Earth is flat. I mean, come on. And it's just really a question of how stupid can they get? And the answer is pretty darn stupid, because if you want to believe the Earth is flat, then one of the things you have to deny is gravity. And they actually do that, and I've got a pair of videos here demonstrating just that. Because if gravity is real, how does a flat Earth work? You've either got an Earth so massive that its gravity is going to pull it together into a spheroid, or it's so light that you just don't have any gravity at all and nothing holds you down. So you gotta deny gravity if you're a flat earther. So here's one. It's called Truth Number 25. Gravity doesn't exist. I haven't even looked to see what the other 24 are. I don't want to know, but we'll look at it. By the way, the only sound in this video is some really god-awful music. I won't play that in the background to spare you from it. Plus, for all I know, it's copyrighted, so... My 7 reasons why I believe that gravity can't be true. 1. In new moon, when the moon is closer to the sun, she should be attracted to orbit around the sun just like the other planets. The moon already is in orbit around the sun. It's just orbiting the Earth as well as the Earth orbits the sun. They're both orbiting together, and the moon orbits the Earth. That's kind of how it works. And I mean, really, anything that's out at this distance that is traveling at that speed, along with us, is going to be orbiting the sun. There's actually another body orbiting the sun in our orbit called Cruithnia. Yeah, I think that's actually how it's pronounced. But yeah, it kind of orbits along this way. Every now and then the Earth kind of overtakes it and yanks it in one direction or the other. So it's kind of a weird orbit, but it is orbiting. So he gives us these graphics to show us how he thinks all of this should happen. Yep, so he thinks that as soon as the moon gets onto that side, it should immediately be yanked out of its orbit of the Earth and start a concurrent orbit around the sun. How's that gonna work? Because, when the moon gets around to that point, it's got a lot of momentum behind it. How's the sun gonna slow down that momentum? And also, orbits don't work that way. If the moon were closer to the sun like that in a separate orbit, its orbital period would be faster. Actually, there is one way this can happen, where you have the Earth and the moon orbiting together like this without one orbiting the other. And that is if the moon is at the L1 point. And that's kind of a little gravitational well. It's a Lagrange point between the Earth and the sun. The thing is, the L1 point is about 1,000,000 miles from Earth. And the moon is just under 250,000 miles away. So it's not far enough for that to happen. And like I said, even if it did, you'd have to arrest its momentum somehow. And how are you going to do that? So, yeah, dumb. 2. We should see in nature that massive objects attract to those smaller. No, that's not how it works. The massive objects and the smaller object both attract each other. And they're going to attract each other to a common center of mass. Now, if the massive object is really, really, really more massive, then the position of that center of mass is going to be a lot closer to that object's center of mass, which is really the case if you've got something huge like the Earth and something much smaller like us. But look at what this guy's thinking. So we got this 500 kilogram weight, and he's expecting all the marbles to just be gradually, attracted to it and just stick to it. Doesn't work that way. We can plug all this into the equation for gravity and see what it should be. For a 500 kilogram weight, and let's say the marble is 6 inches away, here's the equation for that. The gravitational constant times 500 kilograms over 6 inches squared. That's just under 1.5 micrometers per second squared of acceleration, which means that at that acceleration, after 1 second, it will be going at a speed of about 0.2 of an inch per hour. That's not even anywhere near enough to overcome the friction of the marble on the table, or even air resistance. Plus, you have a lot of other objects also exerting gravitational pull, like the room around it, the walls. You're in this massive building. What's so special about this 500 kilogram weight? It's not the only thing there. But there is a way to actually see this in action experimentally. The Cavendish experiment, which has been verified independently hundreds of thousands of times. Not only did they all work, they all showed the exact same gravitational constant. Even Cavendish's original experiment, where he wasn't trying to calculate the gravitational constant, people were able to go back, use his figures, and derive the gravitational constant from that. So, link is in the video info, check it out. 3. All planets should be like flies stuck to the sun as we are to the Earth. No. This guy doesn't understand an orbit. So he's got the planets in a tug of war with the sun. That's actually not a bad analogy. And if that's what was going on, then yeah, the planets would crash into the sun. But the planets are also moving laterally. So now imagine that you've got the sun in the middle, and the planets are zooming around it. Right? So the rope is holding them in as the sun pulls them in, but the momentum of their lateral motion is pulling them around in this circle. Now, I'm sure you've done this with your friend. You've gotten a rope or something, when you were kids, and you've run around each other while holding onto the rope. That's what's going on here. It's just since the sun is much more massive than the planets, the sun ends up being the center of it. 4. We should be in orbit around the Earth, just like the sun keeps all planets orbiting around him. Gotta love how he says him for the sun and not it. I don't know what's going on there, but anyway, he doesn't know what an orbit is. If you don't have that lateral motion, then you fall straight down. And if you've got too much momentum, if you're going too fast, you'll achieve what's called escape velocity and go out into space. An orbit is kind of like the sweet spot in the middle. So here I just have a tennis ball, and I can throw the tennis ball around like that. Okay, not very well. They used to say I throw like a girl. No, I don't throw like a girl. Most girls can throw much better than me. But you notice what it's doing. It's coming up in a parabola. Well, they say it's a parabola. You're probably taught in school that it's a parabola. Technically, it's an ellipse. But one focus of the ellipse is way down at the center of the Earth. And that's so far away that for most purposes on this scale, it might as well be a parabola. A parabola would be if the focus is infinitely far away. The equations are a little easier, and it's close enough for most purposes, but the reason why we use the parabola is just because it's close enough and the math is easier. As long as we don't need that level of precision, then we can do that. But technically, we should be using an ellipse. Well, now let's think. If we had this ball freeze at the apex, and then right as it's at its apex, we instantly replace the Earth with a black hole of equal mass, right where the Earth's center of mass is right now. So you've got the same mass, and therefore the same gravitational field, pulling on this ball. What'll happen is it'll go across this part of the ellipse, it'll come back down. When it goes around the black hole, it'll be zooming back around. And so what it'll do is it'll come in a very elliptical orbit around that black hole. And it'll slow down out here and then come in and speed up and then zoom around and come back. And that's what an orbit is. That's how it works. The only reason it doesn't go into orbit from doing this is because the planet's in the way because it's too big. So you need to get this way up high in order to get it into orbit. And you also need to be getting it going fast enough so that it doesn't just fall straight back down. But if it goes too fast, then it goes out into the solar system and doesn't stay around the Earth. So, like on the moon, since there's no air, all you'd have to do is get it higher than the top of the highest mountain on the moon. On Earth, that's not good enough. It's not good enough to get it just above Mount Everest, or actually Mount Chimborazo in Ecuador, for reasons I won't go into right now. because you've still got air, and as it's coming through, as it's zooming through, the air is going to be pushing on it, slowing it down, and then it'll lose velocity and come right back down. So you got to get it up high enough so it's outside the atmosphere and get it moving laterally at just the right speed to get orbital velocity so it goes around. That's how an orbit works. And think about it. Why would it go in this curve? Why would it be curved around like this if there's no gravity? If there's no gravity, it goes off in a straight line. If there's nothing pulling back on it, it's going to go off in a straight line. You need gravity to pull it back. So if it goes zooming off fast enough, the gravity's not strong enough to pull it back. If it's not fast enough, gravity's going to pull it down. It's going to come crashing back to the ground. Right in the middle of that sweet spot is where it's going to get in that orbit. And that's how orbits work. 5. Mosquitoes, ants, and fleas shouldn't move freely while gravity is using all its strength to keep from falling into place. The entire infrastructure of Australia, steel bridges, and heavy concrete buildings, because according to Ballers, is upside down. No. If this sounds confusing, it's because this is a misconception that flat earthers have, that gravity goes in one direction. So kind of think of like the earth as being this rock in a stream and the water's going by the rock. And so the water's pulling everything in one direction. And so if you're on the side of the rock that's facing the direction of the flow, then you can stand there. If you're on the other direction, then you're going to get pulled away by the stream. That's not how it works. Gravity isn't like one direction of the universe that it pulls everything in. It pulls everything towards the common center of mass, and in our case, that's the center of the Earth. So Australia may be quote-unquote upside down in relation to us, but it's not upside down because all the buildings and the bridges in Australia are still being pulled towards that center of mass. So it's being pulled in a different direction. It's all going towards the center of the Earth, no matter where you are. And that's related to number 6 here. If gravity is so powerful to sustain without falling the entire infrastructure of Australia, which is upside down in the southern hemisphere, should not allow the wind to blow away a particle of dust. I have no idea what his conception is here. This little, I hesitate to call it an animation, let's call it a slideshow. This little slideshow he presents leaves me none the wiser as to what his thinking is. 7. If gravity is using a large amount of force to keep the ocean stuck to the Earth so they cannot fly off into space, that's not how it works. The water from a glass, being a very small part compared to the great vastness of the ocean, we should see it concave. Yeah, this is weird. This is exactly the opposite of what most flat earthers say. They say we should see the convex curvature because they're expecting the curvature to be a lot bigger than it really is because the Earth is huge, so the curvature is not that much. But he's thinking it should be concave for some strange reason. And, okay, concave with gravity. Why would it be flat if there were no gravity? Why wouldn't it just float off and form little globules like it does on the space station or the Vomit Comet? These guys have no clue. They have zero understanding of this whatsoever. And here we go to buoyancy. Gotta love flat earthers and buoyancy. Yeah, so a sponge you have to push down, but a rock just falls. What sort of point he's making here, I really have no idea. The reason why the rock sinks while the sponge floats is because of density. So when the sponge is floating, it's displacing a certain amount of water. And the amount of water that it's displacing has the same mass as the sponge does. So what you end up with is an equilibrium where the gravity pulling on the sponge and the gravity pulling on the water equal out. If there were no gravity, again, it would just form little globules and everything would float. And so, I mean, I've heard other flat earthers say this, and I really don't have a clue where they get this from. The reason why the rock sinks is because the rock is so dense that it can't push away a sufficient volume of water to equal its mass. So if the entire volume that it can push away, the entire volume of the rock, doesn't weigh as much as the rock, then the rock sinks. You know, I mean, this is kind of the old, I really wonder what goes through these people's minds. You know, a lump of steel sinks, but you form the steel into the shape of a ship and it floats. Well, because the ship is displacing more water. Okay, so that's the first video. This second video, Gravity Disproven in 3 minutes. It has better production values, but that's about all I can say for it. So let's see what this idiot's doing. Then the simple fact that I can even jump disproves it. How? Okay, let's watch you jump, okay? Here we go. And you're pushing off. Why are you pushing off? If there's not a force pulling you down, why should you have to push off to jump? Okay, and then let's watch you go off into space. Here you are, going off into space. Oh no, wait a minute, you're not. Look at that, you're stopped. You're stopped right up there at the top. Why are you stopping? What stopped you? Uh-oh, look at that, you're going back down to the ground. You went back down to the ground. So you had a moment of upward acceleration where you jumped, but then a continuous downward acceleration pulled you back down to the ground. And that downward acceleration is gravity! Moron! A small magnet overpowers the entire mass of the Earth. Yeah, because magnetism is stronger than gravity. Gravity is a fairly weak force. Yeah, we know that. Why are those at the bottom, those paper clips at the bottom, why are they dangling? Why aren't they all like just clustered around there? Why are they in that downward kind of stalactite formation there? Where is gravity now? Okay, this goes back to the buoyancy thing. The sponge floated because it was less dense than the water. The rock sank because it was more dense than the water, and it wasn't able to displace a lot of water. So now this is a helium balloon, and he has to know that. I mean, he's the one who set all this up. If you just blew up a balloon with your breath, that wouldn't happen. You know what it would do? It would kind of float gently to the ground. So if you dropped an uninflated balloon, that balloon would fall to the ground. If you inflate it, you make it less dense. It's covering up a bigger area. So there's more air resistance when you drop it, so it kind of floats to the ground. But in this case, the fact that the balloon is filled with helium means it's even less dense, and it's less dense than the air around it. So gravity is pulling the air down underneath the helium balloon. And if it weren't for gravity, this wouldn't happen. You know, do it on a vomit comet and it just kind of stays there. It's because gravity is pulling on the air. And so what's going to happen is, I mean, it's not going to fly out into space indefinitely. It's going to fly up to a certain part because as you increase in altitude, the air gets less and less dense. So there's going to be one part where their densities equal out, and the balloon's just going to hover there until it starts losing helium, and then it's going to come back down again. Yes, it does come back down because of gravity. But that where the densities are equal, that's called neutral buoyancy. And you also see that in fish. Fish tend to be neutrally buoyant because it makes them better able to swim up and down. So, yeah. So let me just show you my Galilean thermometer back here. And this thing's pretty cool. Galileo knew about density, of course, and he discovered a lot of these principles. And he knew about the concept of neutral buoyancy. And that's what this thermometer exploits, because here we have a liquid, and the hotter that liquid gets, the more it expands, and when it expands, it becomes less dense because it's the same mass. So what we have here is a lot of these floaty hoobie-heebies. Yes, hoobie-heebies, that's the technical term. They're all at different densities. So down here, we have some that are denser, and they get less dense, and this one up here at the top is the less dense of all. I don't know if you can see it, but they all have a number on them corresponding to the number of degrees it is when they're neutrally buoyant. So down here we have 70 and 72 degrees. Up here we have 74 degrees, right? So I'm trying to see how it behaves when it floats around. It looks like it's fairly neutrally buoyant, so maybe it's 74 degrees. It might be 73 or 73 and a bit, but it's definitely over 72 because 72 is way down here. If it cools down below 70, then these two will float. It goes up. 82 is the highest one here, so if it's 80, then this one will be at the top, this one will be somewhere around the middle, and the rest of these will be at the bottom. And that's how density works, and that's how you have things like helium balloons floating, balloons that are filled with air just gently floating down, and then if you just drop an uninflated balloon, it just falls to the ground more quickly. It's all about buoyancy, and it's all about the air, or in this case, the liquid, pushing back up on it as gravity tries to pull it down. It's all about gravity. And that's why Galileo was awesome, and flat earth people fail hard. Why isn't gravity pulling it down? Looks like it is to me. Are you seeing the string? Do you see the string? Gravity isn't pulling the balloons down because they're less dense than the air, which gravity is also pulling down. Pushed down from above, not pulled or sucked from below. You know what that means, right? No, this makes no sense. I don't even have any idea what his thought processes are here. This is a pretty cool demonstration when you let go of the slinky and the bottom of the slinky stays where it is until the top comes down. I mean, if there's no gravity, why is the slinky being pulled down? Why can't you do it with the slinky being pulled left or right or whatever? So, no, it's not pushing it down from above. What's happening is, at the bottom, the reason why the slinky isn't being pulled down any more than it is because at that point, the upward tension from the spring equals out the pull of gravity from below. So that's what's happening there. Gravity seems to be very fickle and selective. Oh, God, here we go. I just explained this, people. This is the buoyancy stuff again. Density and buoyancy, not gravity. How is it going to work without gravity? On a vomit comet, they would just kind of float around. They would all be kind of neutral. And the liquid would just kind of, pull up into little globules and everything. You can do this yourself. It'll cost about $5,000, but you can go on a ride on a vomit comet for that. Try it yourself. When you're on the airplane normally, then you've got your uninflated balloon, your air balloon, and your helium balloon. All the different buoyancies. The helium balloon goes up. The other two go down, but not at the same rate. Once you're in microgravity, once you're experiencing hypogravitic effects, they're all just going to float around. That's what happens without gravity. Idiot! Also, should you really be driving like that? That seems kind of dangerous to me. Yep, this is their best proof. This is the best they can do. Pathetic.